Hi, everybody. I know. Oh, thank you for recording me. I appreciate that. I'm Pat Griffiths. I'm also working part-time for Meta. I am theoretically retired, but I'm helping with a lot of the standards work that we're doing in Meta. Past president of SIMD, past president of the Ultra HD Forum, blah, 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 blah. Actually, a long time ago, president of the Consumer Electronics Society many years ago. So it's great to be here. And as I always joke, it's not about more pixels, it's about better pixels. That's why I'm looking forward to this session.
Thank you, Pat. And
I think I went this one.
you did already. Who didn't do?
Hey, everybody. My name is Ryan Lay. I'm currently working in the same team as Yanis and David, mainly focused on the video compression and the processing on the server side.
Okay. I'm Yiling Wang from the Google YouTube. I'm working on the video quality model research and applications.
Hi, I'm Christos. I work in the video algorithms team at Netflix, same team as Pavan on the other side over there. And I work on video quality research, development, and systems across different Netflix domains. Yeah, thank you.
Did you do the intro? Yeah, I did. You did. Only Abhijay. Come on.
Thank you. Hi, I'm Abhijay. I'm from Sony Interactive Entertainment. And I recently joined them. I'm a machine learning researcher over there working on Gen AI evaluations. And I'm also working on perceptual similarity metrics. It's nice meeting you all today.
Thank you all again. Let's start, and we're kicking it off with a presentation part of Sam on fine-grained HDR image quality assessment. We have Mohsen, who very patiently waited for us while we were eating, and it's, you know how late it is in Europe. So Mohsen, floor is yours.
Thank you very much. Hello, everyone. My name is Mohsen Janadile from the University of Constance, Germany. Together with our collaborator, John Snayer from the Cloudinary, we are pleased to present our work on fine-grained HDR image quality assessment. This study is the result of a collaborative effort involving multiple university and industry partner, and was part of the JPEG AIC 3 activities. High dynamic range imaging enhances visual realism by enabling greater brightness, higher contrast, and wider color gamut, far beyond the limitation of the 8-bit standard dynamic range. Recent image compression formats such as JPEG XL, JPEG AI, ABIF, and JPEG XT support HDR content. However, their performance at high visual fidelity, where the impairments are subtle and difficult to detect, is not well understood. Existing HDR datasets are limited in scope for evaluating subtle impairment. They often include only one codec. They use tone-mapped version of the HDR image for subjective evaluation, or are not designed to include distortion level below the visually lossless threshold. As a result, they offer limited insight into perceptual lossless compression range. This work not aimed to compare codec. Instead, our goal is to evaluate the JPEG AIC 3 methodology, a subjective test protocol, and scale reconstruction model for estimating the GND-based quality score for HDR imaging. We also use the generated dataset to benchmark the performance of the existing objective HDR image quality metrics. These are the 5 HDR source image we used. They were selected from 23 candidates by the JPEG AIC group for content diversity. My colleague John will explain the source image creation and the encoding recipes.
Yes, so the images are all in the Rec 2100 color space with the PQ transfer curve using 10-bit precision. And they all have the same dimensions that are fitting on the test displays. If you go to the next slide, the images were compressed using 4 different codecs: JPEG XL, JPEG AI, JPEG XT, and AVIF, at 5 different bit rates, ranging from typically 0.2 BPP to a bit over 1 BPP. For the 3 modern codecs, and for JPEG-XT, higher bit rates were used in order to match the quality range. The bit rates were selected depending on the source image in order to get an approximate quality ranging from quite distorted, around 3 or 4 JNDs, at the lowest bit rates, until well below the threshold of visually lossless at the highest bit rates. So in total, there were 100 different test images for codecs, 5 levels, 5 sources. And all of the images, both the originals and the distorted ones, are represented as 16-bit PNG files, so they can be viewed in the Chrome browser, which was used in the testing environment. If you go to the next slide, yes, back to Mohsen.
Thank you, John. For subjective evaluation, we use the JPEG AIC test protocol that Dietmar explained yesterday, I guess. Which combine the plain triplet comparison, which the image are side by side, 2 images shown, and the user can toggle between them and select the image with the lower quality. They toggle with the reference. And boosted triplet comparison, that each image were zoomed with factor of 2 and flicker with 10 Hertz with the reference. We didn't use artifact amplification for the HDR image because we were not aware what that amplification of this artifact would be for the image. So we used only zooming and flicker test. So we evaluated all the, we generated a triplet for all possible of triplet with the same codec comparison. So for 30 same codec for BTC and 30 PTC triplet per codec, and 20% cross codec we included for alignment. Therefore, 144 BTC and 144 PTC triplet per source we created. In total, 720 triplet for each of the test conditions. We divided this triplet to 6 batch of 120 question, but in this division, each triplet and the reverse were in the same batch for consistency calculation. The participants were different for the BTC and PTC experiment, and we allowed each participant to complete only 2 batch of 120 questions. So can complete 1 or 2. To configure the or experiment for the calibration, we followed this to the BTC 2100 and BT 2246. We set the incident light to 5 lux, and the viewing distance for the BTC, which is 4K, cover the 4K screen, it is 1.5 the height of the stimuli, and for the PTC, which is cover only about full HD from the screen, so the viewing distance is 3.1 the height of the stimuli. The experiment were conducted in 4 labs. For consistency, we made the operating system to be fixed using Mac OS version 15.0 or newer. In 3 labs, Constance, EPFL, and IT, we use MacBook Pro model 2021 or 16-inch or newer, with liquid retina XDR display. The display was set to the native resolution, with peak brightness was set to 1000 nit and SDR wide to 100 nit. This allows for 3.2 headroom stops higher than the SDR wide. And the color profile was set to the HDR-P3 and refresh rate to 60 Hz. In one lab that they have this BBM HX310 mastering monitor, which is very expensive monitor, I think 25K. This also is set to for native resolution, and because they use HDMI 2 to connect it to the Mac Mini, We set the refresh rate to 30 Hz to avoid chroma subsampling. The luminance was also calibrated similarly. We use Google Chrome version 134 or newer, and the image was shown in 1 by 1 image pixel to the native resolution. In total, we had 151 participants in 4 labs, 3 countries, and each lab collected 25% of the responses for the BTC and PTC. The average duration per batch, it was 220 minutes and for the PTC and about 11 minutes for the BTC. In here, this table shows that when the difference between the distortion level increased, the accuracy also increased. The accuracy and the ratio of the correct responses increased, which is as expected, and also the ratio of the natural option decreased when the difference was more obvious. So in total, we had 34,560 responses from 144 batch for each of the experiment. And we use, again, JPEG AIC 3 methodology for filtering that Dietmar explained yesterday, that we calculated the accuracy and consistency. Accuracy, it was if 2 test image compared, if the user select the image with lower bitrate for the same codec, we assume this is a correct response. And for consistency, because we have the mirror of each triplet, so if the user answer based on that, there is measure for consistency, we have that Dietmar explained yesterday. We use a threshold of 0.7 for filtering, and after filtering, we kept 142 BTC and 134 PTC batches. Again, we use the JPEG IC reconstructed reconstruction model that combine using maximum likelihood estimation to fit a unified model, an exponential rate distortion function, and quadratic boosting between the PTC and BTC. This is the model that Dietmar yesterday in talk 118 in detail explained it. And we use this, so in here you can see the exponential rate distortion function. It is ranging for different codec from 0 GND to 56 GND. And as you can see, we calculated also the 95 confidence interval by bootstrapping the responses and running all this procedure that I explained. And then the 95% confidence interval is shown in the shaded area. As you can see, the average length of the confidence interval at 1 GND is about 0.27 GND, which shows very precise estimation of the GND. We evaluated several SDR and HDR metric in our data set. John will explain this slide.
Yes. So we looked at some classical SDR metrics in 2 different ways. One just giving them the PQ image, and the other first doing a tone mapping to SDR and then comparing those images. So none of the SDR metrics perform very well, but many of them do perform better when they work with tone mapped images, probably because they're designed for SDR images. We looked at the overall correlations in terms of Pearson and Spearman correlation coefficients, but also at the per codec and per source correlation. So per codec is actually the average of the correlations you get if you only look at the subset for a fixed codec. Per source is the same where you fix the source image and only look at that subset. So those correlations are always higher. Per codec correlation is particularly useful if you want to use a metric to set a quality level where it's not so important that it can avoid codec bias. The per source correlation is particularly useful if you want to use a metric to do codec comparisons where it's not so important that there might be a source bias. So if you look at the HDR metrics, the correlations are better as expected. And the one that performed best amongst the ones that we tested was HDR VDP2, which had the highest correlations both overall and also per codec. But there's other metrics like PU2, IW, PSNR that performed quite well, and Budger-Oakley and Simulacra 2. So these are, of course, just overall correlation coefficients. So you can also look a bit more in detail what the actual correlation looks like by plotting the metric versus the subjective scores. So in these plots, every line corresponds to a specific source image and a specific codec. And here they are colored by codec, and the line style indicates the source image. So this produces a kind of spaghetti plots where a well-correlating metric will have all of the lines close to one another, whereas metrics that don't correlate that well will be more spread out. But you can also notice on these plots the biases that a metric might have in terms of the source image or in terms of the codec. For instance, the flower image was one that consistently received lower scores than the other images in many metrics. For instance, the JPEG XL codec was also typically receiving lower scores in most metrics. And so these plots help to interpret the metrics, to get an idea also of how to map the metric scores to the actual JNDs, but also to discover these biases that still might remain in a metric.
Thank you, John. As you saw in the previous slide, for some metric, the correlation value are very close to each other. To statistically compare this correlation to test if the difference between them are statistically significant, we use the Meng, Rosenthal, Robin, or MRR test, which is used to compare two correlations that share a common variable in psychophysics. We want to test whether metric X and metric Y are equally good at predicting the subjective score Z. So we set the null hypothesis that the correlation between X and Z equal the correlation between Y and Z. To test this, we compute the Z statistic, where the numerator is Z1 minus Z2 are the Fisher Z transforms of the two correlation variable, and the denominator adjusts for how similar X and Y are, since they both relate to the Z, and H is correction factor for the dependency. After computing the Z statistic, we use a two-tailed test at a significant level of alpha 0.05 to decide if the difference is statistically significant. Here is the result. Each cell tells whether the raw metric significantly outperform 1, underperform -1, or ties 0, the column metric. HDR VDP2 consistently outperform all the other method, and after that, SSIM Ultra 2 perform the best between the metrics. So in conclusion, the study demonstrates that JPEG IC methodology enable accurate subjective quality assessment for HDR content. With the study we conducted showed that the average confidence interval at 1 GND was 0.27, which is very precise estimation. The resulting HDR data set is visible to imperceptible distortion from about nearly 0 to about 5 GND, and is suitable for the benchmarking HDR capable codec and metrics. Evaluation of objective metric reveals that STR metric are not suitable for HDR content, even with tone mapping. Some HDR specific and perceptually optimized model like HDR VDP2 perform well. However, even the best metrics still have some source and codec bias. Therefore, careful subjective evaluation is still required for reliable codec evaluation and quality assessment. In the future work, we will also compare the responses we collected in different labs to see if there is any difference between the responses in this different lab. And also, we conducted the experiment in partially controlled environment in Cloudinary and Huawei. In Huawei, it was a lab, but the ambient light, it was not fully controlled, and the incident light, so it was a bit changing for different participants. In Cloudinary, people did use the MacBook Pro 16-inch in their living room, but with recommendation to have like dimmed light and so on. But the responses are not enough to, therefore we didn't include in this study so far. The data set right now, we submitted this work for a conference and we're waiting for decision. If the paper will be accepted, we will publish the code and the data set in this link. Thank you very much, and we are happy to answer your question.
Thank you, Mohsen and John. Apologies for not announcing. I know it's very late also for you. Great work. Opening up for questions. I see Cosmin.
I do have one question. So you mentioned that the range of distortion is going to span from visible to imperceptible. If we look at the metric correlation over just the visible end of the spectrum and we ignore the nearly imperceptible, does that change the correlations meaningfully?
You mean in here in this slide to include only, for example, distortion level that they have this GND higher than 1 GND, let's say?
Yeah, as an example, the idea being that like in the practical range of the curve, if you will, where we care about meaningful quality differences, is the metric good enough in that range? If it's good enough in that range, the fact that it fails in the nearly lossless domain is interesting, but it doesn't mean that it's not usable in practice. Where if it also fails over the useful range, then the metric is somewhat useless for HDR and we shouldn't use it at all.
And if I may, thank you. I was about to ask the same question, but I knew that it would come from the audience. If you go to where you have the metrics and the JND, you have this other plot, no, the many plots for the different metrics. Like here, for example, I'll pick one. I'm not trying to defend VMAF. All I'm trying to say is that it's known that after, say, a value of 93, it's uncharted territory. So one could cut I'm not sure if you can see where I'm pointing. You can cut and try to fit the range where a metric is at least validated, right? Let me put it this way. And the same applies to other metrics as well. I know in particular, HDR VDP is targeting very close to the perceptibility level. So the key question is, did we find a range of qualities that maybe, I don't know, in the low range, PSNR is ideal, right? In the middle range, SSIM is ideal. In the high range, HDR VDP is even better, right? Did you do a quality range analysis?
I think that's a good question for future work to split it up into different segments of quality. But you can see in these plots, if you chop off the part below 1 JND or below 2 JND or whatever the threshold is, you can still interpret the plot and get an idea of the consistency, but it could be summarized by computing the correlation coefficients for subsets of the data. That's
exactly, yeah.
It's a good idea to do this. Yes.
Thank you. I see Patrick.
If you look to the value for the lower than 1 GND for the VDP2, you can see that probably they have different trend for the nearly visually lossless than the other.
Yep. Patrick?
Yeah, by the way, correlation coefficient it might be not the right way to measure in such narrow range of quality. So if you go for quality range analysis, you should use something else like AUC analysis, like the Krasula framework and so forth. And I have questions because which version of HDR VDP2 were you using?
2.2.2.
2.2, okay. And then you pay attention to existence also for HDR VDP3 to have the right model of the display in terms of luminance and everything, right?
We set the display exactly as the MacBook Pro 16-inch with the viewing display for the PTC.
Yeah, and the luminance range also, which is very important. Also, okay, so interesting to see that still HDR VDP 2.2 is working well. I have a minor things that I didn't get quite well because you have two type of display. You are using native resolution, and then you have different aids, and I'm not sure I get exactly what is a viewing distance you apply. There was a 3.1 viewing distance.
I think there is content. I'll let the authors respond.
Yeah,
I'm saying that there is HD content and UHD content, right?
Well, there's two protocols, and in the JND units correspond to what would happen in the plain triplet comparison.
Yeah, but that's okay. No, I get it now because I missed this information. It was really the stimuli helps, and because you are native resolution, that works. Okay, because I missed when you presented that you have different display with different resolution. So just want to make sure we are talking about stimuli helps. So that's okay, good.
Thank you. Any other question for our presenters before they can go to bed, I guess? Okay, hearing none, thank you one more time.
Thank you.
Work. Looking forward to publishing and getting those data sets for more researchers to use. Okay, and now we are switching gears again. We have our, I think, last ETG presentation. And again, I'm quick reminder, ETG is new stuff, right? Not traditional stuff that we are dealing with. And we have Frosov who will be presenting. I'll let her introduce the topic herself.
So, hello, my name is Efrosini Dutsi, and today's presentation is something different. Well, it goes beyond the pixels and the way we are dealing with the visual information right now. I'm working on image and video compression that is motivated by the brain. And here I'm going to explain that these models coming from neuroscience could be beneficial not only to the processing of the information, but also for the assessment. But let me begin by the fact that we are all aware that the cellular data consumed per smartphone per month is exponentially increasing over the years. So we have 21.6 gigabytes on the left. And if we consider the total amount of information on the right, this is approximately, for all the different apps that people use, it's approximately 147 exabytes. 80% of these data are generated by apps related to videos. So we need to deal with the visual information and find the best trade-off between bitrate, quality, and efficiency. And if for some reasons we need to sacrifice the efficiency of the algorithm, of course, we have higher bit rate. And if we pay more attention to the efficiency of the algorithm, the bit rate is reduced, but of course, we have a higher computational cost. So the project I'm working on is called Brain Code, Brain-Inspired Intelligence for Semantic Video Compression. It's funded by the European Union under the framework of the Marie Curie Skłodowska actions. And so the goal is to develop new compression algorithms that mimic the structure that computational processing of the brain. And what really matters for us is these algorithms to be content aware. And by saying content, I mean, for the brain, what matters is what really changes in time. This is what is encoded. And so everything that changes should be encoded, and everything that doesn't change has been captured in the beginning, and it remains constant until something new happens. So we all know that the brain is a super processor, and it doesn't consume a lot of power. So it means that this kind of algorithms are gonna reduce the computational cost, because this is a completely different kind of processing. So what we are doing now is the frame-based processing. So we capture all the frames in time, and then we try to get rid of the spatiotemporal redundancy. However, the brain doesn't work like this. So the brain captures what really changes in time. This is related to the, as it is called, event-based processing. There are sensors that capture the information that is like this. And this is how we also process the information. But let me go a step back and explain a little bit the biological framework. So this is the brain. The visual information is captured by the inner part of the eye. It's called retina. It's a multi-layer structure of different kind of cells. So these cells in the beginning transform and then encode the information into a sequence of spikes, as they are called. So these spikes are simple events, and these events are similar to each other. So the only information that really we should pay attention on is when these events happen. So this is the processing unit of the brain. This is a neuron. The neuron consists of the soma, where all the processing happens. It receives the signal from its neighbors through the dendrites, and if something really important happens, the neuron fires its own spike, so encodes the information. It has to transmit this information through this cable, the axon, to the rest of the neurons. So the neuron has been approximated by an RC circuit. So a circuit that when it's flown by a current, there is a resistor and a capacitor. And once this current is strong enough, the capacitor is full, and then a spike is generated. So this is how it works in general. This is a neuron. The neuron receives some spikes from its neighbors. This is the first spike is going to reach this neuron, and the neuron is going to be excited. This is called also depolarized. Okay, so until the next spike that will arrive, there is a hyperpolarization process, and then it is excited again until it reaches an upper limit, a membrane capacity, and then it has to propagate the information to its own neighbors, okay, through the rest of the visual pathway. So it fires its own spike, and it's propagated through to all its neighbors. So in practice, we have frames, okay? So here we see a sequence of frames with different color intensity. The lower is the second one, the higher is the last one. And what we do is the first row, okay? So for this red block, we need to generate a binary code, and this is what we store or we send, okay? But the brain does something different. What we really need to consider is some time instances. So you see these dashed lines, vertical lines that correspond to its different frame. So there are many different ways to generate the spikes, but the challenge is how to interpret this code in order to reconstruct the information. And so this is what I'm going to mention right now. So we could either count within this time windows, count the number of spikes, and then you see that, for example, for the lower intensity, there's a single spike. For higher intensity, there are more spikes. Or we could use another approach that is related to the time to the first spike, the TTFS. So the higher the intensity is, the sooner the neuron is going to be excited. So we are going to have the first spike. And for very low intensities, we could have at the very last spike generated spike, or maybe no spikes at all. And there is a third way also. This is the temporal contrast. It's the temporal contrast that it's somehow related to the process that we are doing when we compare the frames. So here in continuous time, as we see over here, we see the change of the intensity. And so each time this change reaches a threshold, a spike is propagated, is generated. And so if there is a decrease, we have a negative sign. If there is an increase, we have a positive sign. In general, there are two main groups of interpreting this different way to encode the visual information. And this is the rate coding and the temporal coding. Let me go to another aspect. So spikes are used for many different applications, except image and video compression. For transcoding, of course, because as a process is going to reduce the computational cost. That has been very efficiently also applied to reduce the computational cost of CNNs that have been converted to spiking neural networks. And of course, people were not only interested in reducing the computational cost, but also having high accuracy. And for many different learning tasks and well-known data sets, when this conversion happened, we had state-of-the-art results for classification, for detection, object tracking, and state, many other. And of course, spikes are nowadays used for the neuromorphic computing. So we have hardware that can support this kind of process. In our case, for image compression, we had a paradox that we've done all this process, we generated the spikes, we count the number of spikes, and then in order to evaluate the algorithm, we had to go back and generate the binary code. We did this with an adapter quantizer. We merged the TTFS and the rate coding, and things were much worse for the quality because we had to use the standards, PSNR, SIM, and maybe also no reference. We use BRISC, for example, that maintains the natural quality of the images. But this is not what should happen. And it's not only for our case that we do a bio-inspired processing, but models coming from neuroscience should be considered in much more when we do the image assessment, because finally, the way the brain perceives the visual information is the most important one. And what we try to model when we do the subjective test. But nowadays, we really have models that describe what the brain perceives. And of course, I can't mention everything, but I can give you just a simple intuition of some algorithms proposed, well-known things nowadays. So for example, in the very beginning, we are aware that the brain only captures the low frequencies of the signal. And as time increases, higher frequencies are extracted. And so the signal and what we perceive and understand is enriched. That has been framed as the retina, and well, we proposed the algorithm a few years ago as the retina-inspired filter, a filter that mimics what happens in the very beginning of the visual system. And it's nothing more than a simple Gaussian in the very beginning that turns into a difference of Gaussian with some changing weights. And you see the shape of how this filter evolves in time on the left. And finally, as a step one, this is at the very beginning of the process. This is how it works. In the very beginning, we have just few features extracted, but still we understand the main information. And as time increases, so we go from 26 milliseconds to 41 milliseconds, we have a full description of all the ages and all the information of the object, of the young lady. Later on, for example, we are aware that the V1 has been approximated by the Gabor filters because the brain starts to be more, starts to select better the information that is going to be captured and encoded. And of course, we always need to pay attention that a simple change at the neural code doesn't signal anything. It should be a population of neurons that changes, and the activity of a population of neurons that should signal that something has changed here. So in our case, what we are thinking is to statistically compare the distribution of the spike trains in order to evaluate and to measure the quality of the algorithms. I will sum up by saying that understanding how the brain perceives the visual information is very important, and it could be beneficial not only for processing the visual information, but also for assessing the quality of the algorithms. And that quality metrics should, well, at least in our case, but I think we could in general consider this kind of models coming from neuroscience that better describe what really perceive and the selectivity of the neurons and the whole processing that happens in the visual pathway. So this is all. Thank you very much for attending, and please, I will be happy to answer your questions.
Thank you, Froso. So opening up for questions.
Thank you for an interesting presentation. Something maybe I missed that, but I understood that your spikes didn't have polarity. They were just spikes, not spikes with plus or minus polarity.
There could be some models that have polarity, like the last one.
Yeah, because I am much more familiar with event-based cameras, where you have polarity, and you
that could
obtain
be
the
easily
image
added.
just an integration of the different polarities received.
That could be considered into a model to have the polarity also. I just mentioned the basic ones.
Now, you mentioned TTFS, that was the first one. Thank you.
And Naim?
Sorry, so your neurons is from the visual, right? Visual part, that how they are activating and how they are behaving. So do we have a mechanism to measure the level of activity and how many neurons you are looking forward for? What is the population that you are considering here? Or it's
Well, I'm not doing this kind of test. These tests are done by neuroscientists. So they, gives us hearts and so measure the activity and then try to, generate a model that corresponds to this activity. So most of the times there is a small area, it's called fovea, that is the one that they really pay attention to.
Is it Pat?
Yeah, thank you. Interesting presentation. So could you imagine this going forward, dealing with things like color? Because we have different detectors in our retina and those signals go back. Have you been able to identify the paths that different colors take, or is it still in the early days.
I've never used color for these simulations, but I know that inside the retina, the great majority of the neurons are dealing just with the intensity. So
I think that's mainly the rods. The cones actually do the colors.
yeah, yes, exactly. But the great variety are
Yeah, so basically the fovea is mostly tricolor, right? So you have the three types of sensors. It's outside the fovea where you have the brightness, but yeah. We do have, maybe I saw briefly Balu showing up. I'm not sure if there is anything online, but we are almost at time for our break. But any more questions, feel free to ask our guest. I see Patrick, a question or now or during the break? Now, why not?
Don't mind, because if we come, of course, there is the color things, but I think it's not such a problem, right? Because it's overall, it's just a combination of different cones, and you can always do difference, polarity, whatever. So you can always do this type of combination using the spike net. I want to come back on the quality problem. Because in the previous talk, we could see the GND models like HDR VDP, or the VDP, Visual Difference Predictor, and maybe it's a way to go to bridge the gap between spike net and quality, because as you were, as far as I have understood, your proposal was to go to V1, and V1 is, I think, a good foundation of VDP model. So that's maybe the way to go from, let's say, more what we had in the early 90s, let's say quality metrics for GND based on human visual system, but mostly modeling V1 and maybe what is behind, but we are missing the sensor part. And this is where I see a
that
link.
as a combination of all these tests. For example, if we had a network to train, that would be different hidden layers with different kind of sensitivity filters applied to the learning process. I would see something like this.
So it might be the way to go and get out of the supraphysical metrics, let's say top view from, or where the human visual system is seen from the top-down approach like SSIM or other things like that. So maybe that's the way to go.
Thank you for the remark.
Thank you, Patrick. Any other question? All right, so we have this is, again, it predates your involvement, but Naim was one of the chairs of the group formerly known as Sci-Fi QA that did quite a lot of experience, including EEG, right? Yeah. So maybe during the break, you can give some pointers as well. All right, so we adjourn, we come back sharp at 3:30, we have a panel, okay? I'm gonna set up the chairs here for the panelists and the moderator. Please be back by 3:30. Do not roam around by yourselves, okay? And let's stop the recording.